Okay, so this next one involves two different formulas that we need to use. So let's just think about this. If an object has a weight of 700 newtons on the surface of Earth, what is its weight at this other distance? So how I'm going to divide this up is I'm going to take the surface information and the at a distance information and kind of make two categories, because that's helpful for me to kind of distinguish what's different. So it says that I'm looking for its weight at a distance. So weight, that's Fg, right? Fg is weight. So I'm looking for Fg at a distance. And the distance it tells me is, my r is 6.37 times 10 to the 6 meters. Okay, so I'm just kind of organizing everything I know. And then at surface, it tells me that I have a weight of 7.0 times 10 to the 2 newtons. All right. Regardless of if you're at the surface of Earth or in space or on another planet, what has to be the same all the time of, say, U? What needs to be the same? Mass. So you can use mass back and forth. Okay, wherever you go, whatever object you're using, you can assume that you can use that same mass. So here, I'm going to find my mass. Because I know at the surface of Earth, G is equal to 9.81 meters per second squared, always, on the surface. So I'm going to rearrange and solve for m to figure out the mass of this object. So my mass is 71.3557 kilograms. Now, when I think about this, it's like this is my mass too. This is Earth. Basically, this is Earth, not E, M subscript E. So M little e. And then here, there's another object. Just kind of, it's left now. So this is now, this is like your M1, and this is your M2. So since I have both masses, I'm going to use the formula that we had used before when I'm figuring out Fg. So the formula, so the formula I want to use is Fg is equal to big G times M1 times M2 divided by R squared. So Fg is equal to big G, which is our constant, 6.67 times 10 to the negative 11, times by M1, which I figured out here, is 71.35, etc. kilograms, multiplied by the mass of Earth. So that's on my data booklet. 5.97 times 10 to the 24 kilograms. This is all divided by RT squared, because I need my total distance, which I probably should have done before this. So I'm going to find out my RT. So I'm just going to back up a little bit here. Because really, what it's saying is from this distance, that's from like the surface of Earth to here, but I need to include this distance. So I need my whole RT. So RT is equal to this R, 6.37 times 10 to the 6 meters, plus the radius of Earth. which is 6.37 times 10 to the 6 meters. So my RT is equal to 1.274 times 10 to the 7 meters. So that's the radius that I'm going to, or the distance that I'm going to use here. So make sure if you're doing it all in one step that you put everything on the top of the fraction in brackets, and you put the bottom of the fraction in brackets as well, with the squared in the bracket. So you should get on your calculator 175.06 newtons. To sig digs, we'll place this as 175 newtons. So don't flip it yet, I just want to think about this logically for a minute. So on Earth, it told us that Fg was equal to 700 newtons. And then away from the Earth, we just calculated that it was 175 newtons. Does that make sense? Huh? Yeah, it does. So that's good. Sometimes when you're doing physics and you're not sure if you did it right or not, it's sometimes just good, just think about it logically. Okay, so note Fg and G should decrease with distance. Therefore, this makes sense. Right? If I got a way bigger number than what I started with, that should be kind of a warning sign to be like, I probably did something wrong. Right? So you can just stop and think about it logically to see if it even makes sense to you.